Hello everyone. Today we will discuss about the electrical conductivity of metals. So we have studied about the basics of free electron model. So though a metal is a crystalline, it has got many properties like electrical, thermal, specific heat, etc., which are majorly determined by the free electrons. So this we consider the free electrons as electrons which are free to move around inside the metal except at the metal boundary. So this is kind of an electron gas which is more related to the ideal gas, except that this gas will that will satisfies the Pauli's exclusion principle, so that the distribution will be based on Fermi-Dirac distribution statistics, whereas in ideal gas, it obeys Maxwell-Boltzmann distribution functions. So now we'll study the electrical properties of this material, metallic compounds. So metals, we know that metals are very good conductors. So we let us consider as behavior of a single electron of electronic charge minus C and mass m. So let us consider what happens to this single electron on application of an electric field. So here we are considering a purely classical law, that is Drude theory of electrical conductivity. So in the absence of an electric field, electrons, we know that the electrons are moving, the electrons are freely moving inside the metals within the boundary of the metal, but the net velocity will be zero because it is the random motions in the absence of an electric field. Since velocity v is equal to 0, the current density J is equal to charge into velocity, so minus E into V, that will be 0 because velocity is 0. Now we consider the application of an electric field E, so that there is a drift of electrons. This is like initially the electrons were having a random motions, and on application of the electric field, it has got a directionality, so it will be drifting towards it will be the in opposite direction to the electric field, so it will be drifted towards one directions. So according to the Newton's law, we can write this ma, that is m dvd by dt is equal to charge into electric field, where this velocity vd is called the drift velocity. From this equation we can take the integral, so that we'll get the drift velocity value, that is this term minus e et by m, plus there is a constant, integration constant, that is the initial velocity. But we know that the initial velocity is 0 because in the absence of electric field, the velocity is 0. So we can neglect the that constant, so that this is the value of drift velocity, and the current density will be charge into velocity, that is minus E into drift velocity, that will be E square times E by m into t. So from this formula we can say that the current build up as time passes, so that the current is increasing monotonically with time. So this is like current, if you applied a finite electric field, after some time, sometimes the current is increasing, so it keeps on increasing, so it can go to infinite value. But we know that this is not going to happen, so there will be always a finite current when we applied a finite electric field. So that means we are missing something here. So that is because we didn't consider other effects like scattering of electrons. So we need to consider that. Also there are defects such as imperfections inside the crystals. There are grain boundaries. There are positive ions, and there are also impurities. These can cause scattering of the electrons, drifted electrons. So there is also thermal vibrations. So the ions will exhibit thermal vibrations, and the quantized form of thermal vibration is called phonon. So this phonon scattering increases with temperature. So after some times this distribution, there will be this disturbed distribution relax back to original distributions. So that is this is based on a relaxation model. So if we take a relaxation time tau, which is called the characteristic time in which the drifting electron relax back to equilibrium state. This can be mathematically represented like this formula, that is d derivative of drift velocity is equal to minus Vd by tau. So this will give the drift velocity which decreases exponentially with time. We can write this formula so that there is a relaxation time which is called the characteristic time in which the drifted electrons relax back to an equilibrium state. So for t equal to tau, the velocity of the directional motion decreases by 1 by ETH of its initial value. So that is how we define the relaxation time. There is also another term called mean free path. So the electron in metal moves along straight line until it collides with lattice imperfections. So the average distance that electrons travel between two successive collisions is called the mean free path. So there are two processes. We need to consider these two processes. One is because of the drifted electrons under the influence of electric field. Also there is scattering. Due to scattering, this drifted electron will be relaxed back to its equilibrium position. So this we in the Newton's law of motion, we have to consider this additional term, so that we can write the steady state equations, that is this dvd by dt is equal to 0. So that gives the steady state value of drift velocity. From this formula we can get minus e tau by m. Consider there are n is the electron concentration, so that the steady state current density J is given by n into charge into drift velocity. So that is minus NeVd. So on substituting this Vd here, you will get Ne square tau by m into electric field. So in general, J can be expressed as sigma into E, that is called the Ohm's law. So we can write from this formula, we can write the expression for current, the electrical conductivity, that is sigma is equal to Ne square tau by m. So this is the root expression for electrical conductivity. From this formula we can say that having a concentration n of conduction electrons, each carrying a charge E and mass m, which are drifting under the influence of electric field, getting scattered by various scattering agents and relaxed by characteristic time tau to equilibrium state. So the electrical conductivity can also represented as n into E into mu, where mu is called the mobility, which is actually the drift velocity per unit electric field. Vd is equal to mu into E. So that the mobility can be expressed as mu is equal to, from that previous expression we can write this is E tau by m. We can also express the resistivity as 1 by sigma, that is 1 by inverse of electrical conductivity, that is given by m by Ne square tau. So the electrical conductivity depends on number of carriers per unit volume, that is the concentration n, as well as the mobility. The dependence of these quantities on temperature determines the electrical properties. For example, in metal, the n concentration n is a constant, but mu varies relatively slow with temperature. But in the case of semiconductor, On increasing temperature, the carrier concentration increases exponentially, whereas in the case of insulators, the exponential growth is happening for mobility mu. In that case, n is a constant. So this this expression basically define the electrical conductivity, which is very well in agreement with experimental data, although it is a classical formulation. So based on this, you can work out these two problems. I have given the answers here. So if you have any difficulty, please comment to this one so that I will explain to you how to do this. So there is another, after this, we are going to Wiedemann-Franz-Lorentz law. So the electrons, we just learned that the electrons are responsible for the electrical conduction, which are also responsible for the transport of thermal energy. So this Wiedemann-Franz law states that the ratio of electronic contribution of the thermal conductivity, which is expressed as kappa E, to the electrical conductivity. So the basically the ratio of electronic contribution to the thermal conductivity and the electrical conductivity of a metal is proportional to its temperature. So that is K by sigma is proportional to temperature, and the proportionality constant can be represented as L, which is called the Lorentz number. So basically this observational law is based on Wiedemann and Franz, who in 1853 reported that the K by sigma, that is the ratio of the thermal conductivity to electrical conductivity, has approximately same value for different metals at same temperature. Later on, Lorentz in 1872 find out the proportionality constant, that is L, and this is the expression, that is pi square by 3 into k square by E square, which is called the Lorentz number. So altogether this is called the Wiedemann-Franz-Lorentz law. So the electrical we discussed about the electrical conductivity. So the resistivity is actually the inverse of that. So this is the expression for electrical resistivity, that is m by Ne square tau. The electrical resistivity of any metal depends on two factors. One is the lattice vibration, that is the phonons, which is depending on the thermal excitation, and there is it is also depending on any imperfections like impurities or any defects, can be grain boundaries. So this can also cause the, it can also increase the resistivity. So basically the scattering by impurities is which is actually independent of temperature. So the second function is independent of temperature, whereas the scattering by phonon is purely on the temperature dependent. So we can basically connect this one. The resistivity of metal can be expressed as summation of these two terms. The first one is due to phonons, that is the thermal vibrations, and the second one is we can collectively call due to impurities. So that is because due to the imperfection. So the first term purely depending on the temperature, and second term is independent of temperature. So these expressions, that is this rho, which is splitted into two terms, this rule is actually another observational rule, that is called the Matheson's rule. So we can express this one into two terms. So at very low temperature, we can there will not be any thermal vibration. So we can neglect the term, that is rho, due to phonons, because when temperature is very low, from this expression we can say that this will be tau will be the relaxation time goes to infinity when there is no thermal vibrations. It can the relaxation time is very large. It tends to infinity, so that rho resistivity from this expression will tends to 0. So there is no contribution from the phonon. So it can be purely based on the imperfections. So this is depicted in this graph. As temperature increases, the scattering by phonon becomes more effective, so that the second term, that is rho pH, that is due to phonons, it goes on increasing. So that time we can neglect the contribution from impurities. So the rho is approximately equal to rho pH. So which is increasing linearly with temperature. So this is how the effect of temperature on resistivity. So is kind of an empirical observation which can be used for qualitative understanding of the contribution from different scattering mechanism. But this rule is not always valid. So we should know that this Matheson's rules is always not valid. For example, in the case of when the relaxation time depending on wave vector, we cannot apply this rule. Thank you.